So today let's talk about zero order reaction. It is a zero order reaction. The order of the reaction is zero. Let's take an example of zero order reaction. It is N2 in gaseous state plus gaseous state over the hot surface of platinum, hot surface of platinum or tungsten or molybdenum. Okay, then it forms ammonia. This is an example of zero order reaction. Okay, so let's say a reaction we have A in gaseous state forms B in gaseous state plus C in gaseous state. Okay, initial concentrations are initial concentration. The concentration of initial A is, let's say, small a, and B and C are not present in initial condition. Okay, concentration at time t, concentration at time t, it disintegrates into A minus X, then it forms X and it forms X. Since the stoichiometric coefficient is 1, that's why it's formed S and X and X. So we know rate of the reaction is known as minus d A by dt. What is the value of A? The value of A is minus d A minus X by dt. That comes out to be dx by dt. So rate of the reaction comes out to be dx by dt. Now differential form of zero order reaction. What will be the differential form of zero order reaction? We know dx by dt equals to k into A minus X raised to the power 0. Okay, now we integrate from dx equals to k dt. We cross multiply k over here. Okay, so we get k dt. So here x comes out to be kt plus c, where c is an constant, integration constant. Okay, now we know at time t equals to 0, the concentration x equals to 0, and that's why c equals to 0. Okay, now the equation comes out to be x equals to k t. So this is the x value for zero order reaction. Okay, so if we see the curve between dx by dt versus a minus x, we know dx by dt doesn't change with time. Whatever will be in the a minus x, the power is 0. Okay, so it will be a straight line parallel to x axis. Now if we draw a curve between concentration of product versus time, we know x is the concentration of product that is increasing with the time, and x equals to kt. Okay, here slope is k. Okay, or concentration of product, so concentration of reactant at after time t. So concentration of reactant after time t is a minus x, that is equals to a minus kt. We know the value of x is kt, so the concentration of reactant after time t becomes a minus xt. Okay, now if we come on the curve of concentration of reactant, okay, here if we see the curve between concentration of reactant versus time, So this curve comes out to be like this. We know the concentration of reactant has some initial value and it goes on decreasing with x a naught minus kt. Okay, so now we write the equation minus dA by dt equals to k is to a raised to the power 0. We know it's a 0 order, so that's why k a raised to the power 0. So minus dA equals to k dt. If we integrate these two, we will get minus a at a time t equals to kt plus c. At t equals to 0, at equals to kt minus a naught. So a at a time t becomes equals to a naught minus kt. This is the concentration of a versus time t. This is the relation we will using when we will calculate the concentration of reactant at any time t. Okay. So now let's talk about a new term which is known as half life, which is known as half life. We also denote it as a t 1 by 2 t half. Now what is half life? Okay, time required for 50% of the reactant to disappear. Okay, time required for 50% of the reactant to disappear. Okay, or we can say time when concentration of reactant decreases to half of its initial value. Okay, now in general, half life is defined on the basis of the concentration. When gaseous reaction take place at constant temperature and pressure and volume of vessel changes during progress of the reaction, half-life should be defined on the basis of the mole of the reaction. Okay, when there is a change in concentration, pressure and volume of the vessel, then we will always define the half-life by the moles. Okay, so half-life generally defined on the basis of the concentration. Okay, so if we see what is T half, we know when T equals to T half, what is the value of A? X equals to A by 2, that is the decrement of initial concentration to that by 2. So T half becomes equals to A by 2K. Okay, and T half is directly proportional to A. That is for zero order reaction. We will see a general relation of T half versus A for nth order. Now, right now it is for zero order reaction. Okay, now if we draw a curve between T half and A, if we draw a curve between T half and A, we'll see it is a straight line passing through the center. Okay, completion time. Now we have one more term which is known as completion time. Now what is the completion time? Completion time, as the name says, it is 100% reactant converted into product. Okay, when 100% reactant converts into product. Okay, now we know T equals to T completion when X equals to A. Okay, so T completion becomes equals to A by K. Okay, now T completion equals to 2 into T, also defined as 2 into T half. Okay, so if we draw a curve of concentration of product versus time for a zero order reaction, if we draw a curve concentration of product versus time. Now we know the product is increasing with the linear rate. After a certain time it will start forming and it will be a constant. So this time, this is known as T completion.